Thanks for the invitation. I think I'm the most frequent speaker here. I'm glad to be back. So at a short notice, I decided to talk about some work I've done recently with my PhD student, Irene Gil Fern, and also with Jaehoon and Younjin. So, as the title suggested, this talk will be somewhat similar to what I have given the previous talk. We're looking for some simple structures concerning cycles. We're looking for cycles of different shapes. So let me give you some idea. So the basic setup is we're usually given some density condition coming in the form of a large average degree, say. Then we are asked what kind of cycles you can find. That's basically the question. So one of these classical results back in 1963 by Karate Haino can be phrased in this way. What they prove is that suppose you take any integer k, at least 2, and for any graph G, with the condition that the minimum degree is at least 2k, and the order of graph is at least 3k, then what can you guarantee? They prove that you can always find k pairwise vertex disjoint cycles. So you can have cycles in abundance. K of them, in addition, they are vertex disjoint pairwise. As we all know, if we're given, say, minimum degree or average degree at least 2, which is constant 2, we always have a cycle. So here they say that, okay, if you want not just one cycle, but you want multiple of them, then still minimum degree or average degree constant, which depends on k, the number of cycles you want, suffices to guarantee the existence of such system of cycles. And here this condition 3k is necessary because each cycle requires at least 3 vertices and you want them to be vertex disjoint. Okay, this is one of the classical results. Now you may ask, can we have a little bit more? Because we have k vertex disjoint cycles here, we know nothing about their length. Can we say, can you find something that of the same length? And this is indeed true by Hagwist. So maybe I will start writing here. So in 1985, Hagwist proved that, let me phrase it this way, if you have sufficiently large constant degree, independent of the order of the graph n, then, of course, this degree depends on little k. You can always find k vertex disjoint cycles, each one of which having the same length.
Instead of people, maybe omega 1?
Okay, sure. Maybe more precisely, I should say at least some constant which depends only on k. Okay. Or sometimes when I use this arrow, I mean it suffices to force this structure when it's straight line. But yeah, I think this is more precise. Good. So now we know they are of the same length, and there are subsequent work. It attracts quite some attention. There's some subsequent work of improving this function of k. For example, this bound ck was improved by 1996. This is by Egawa for k at least 3. And then the case where k equal to 2 is by Ostrand. He actually also gave a shorter proof for k at least 3, although the bound comes slightly weaker than the bound by Egawa. And they proved the optimal bound. Basically, they showed that as long as your minimum degree is at least 2k, obviously 2k is necessary because each cycle will require 2 different edges coming out of a vertex, right? We want them to have a vertex disjoint. Okay, let me come back to that. So minimum degree at least 2k, and the order of the graph some constant times k. So, but definitely this linear in k is optimal. This is the improvement. And there are also, maybe let me just mention one more related work. Another related work is now we have the same length. What's other interesting object? Arithmetic progression. And that's indeed done by Ostrand around the same time. So 2002, he proved that there exists a function which is quadratic in k, is enough, for n in g, with average degree or minimum degree at least some constant times k squared. Then you can find k vertex disjoint cycles whose length form of even length, and their length form a k-term arithmetic progression. Any questions so far? Even, yeah, not just, right, of common difference too, yeah, right. Good. So we've seen that there are lots of work done. I just sample a small portion. By no means this is all of the history. But I want to get to today's problem, the question we're looking at, because the proof is not so hard. So I hope to also give you a sketch of the proof to see a flavor of how things like these can be done. So the question we're interested in also concerns cycle. It's called nested cycle in the title. So let me give you the definition. Okay. We say if we have 2 cycles, call it C1 and C2. We say they are nested they form a nested cycle if the vertex set of one of them is a subset of another one. Okay? Let's say a proper subset. So here's an example. You have a outer cycle, what do I use? C2. Then you can have another inner one, maybe with a different color. C1. Okay. So actually, this example I gave, they are also additionally edge-disjoint. So that's the structure we're really interested about. We want 2 edge-disjoint cycles, the vertex set of one sitting inside another. And we're interested in edge-disjoint nested cycles. Good. So now I can state the question. This question was raised by Erd H back in 1975. Erd H asked the following question. He asked two questions. Question one, what density? We've seen that there's so many results where you have the constant average degree suffices for different shape of cycles. Then here, can we do the same? What density enough to force two nested cycles that are edge-disjoint? So in particular, he asked, what is the minimal Fn such that for any n vertex graph G with Fn edges, you can find two edge-disjoint nested cycles. That's the first question he asked. The second question is a stronger question where there's additional requirement on the structure of the nested cycle. He asked about exactly the same. And in addition, there is no geometric crossing of the inner cycle. I will explain what it means. So here, if you see this example here, we have the outer cycle line up cyclically, but the inner cycle, there's no way of drawing them in the way that their edges don't cross each other. So there's a geometric crossing. We cannot draw them both at the same time in a planar way.
So you're allowed to draw the inner arcs outside of the. This is not just a constraint on the order of the vertices.
It's a constraint on the order of the vertices. It's the same thing. So if you can also order the vertices of C1 and C2 so that cyclically they respect each other in order. Yeah. Okay. So here's an example.
So you have to draw the outer cycle really as a cycle.
As really as a cycle. Yes.
Okay.
Yes.
So constraint on the drawing of the outer cycle, you want to draw the inner cycle without crossing.
Or in other words, you can also draw the inner cycle really as a cycle. Then the outer cycle respect the order. They don't cross each other. It's same thing. Different, same thing.
Is it equivalent to it being an outer planar graph?
Is it equivalent? One way is obvious, right? Maybe it's equivalent. Yeah. The union of them is outer planar graph. Thanks. Maybe that's an easier way to phrase it. Right. So here's a, let me draw an example. Yeah, I can draw it here. So here is an example. Nested cycles without crossing. So you have a outside one. Now let's use blue. I have inner one. Something like this. It's outer planar. Here's that word. Is the question clear? Yeah. What is the minimum number of edges necessary to force two cycles, the vertex of one sitting inside another, and they can be drawn in a way that respect each other cyclically. So what do we know about these problems? There is some work done. In fact, the first question is solved already. So this was asked in 1975. 3 years later, Warwick solved the first question. 1978, Bolubai showed that f of n linear suffices in n. In other words, if I just phrase it in the average degree condition as the previous results stated, then for any graph G with average degree at least some constant, for some constant, then you can find two. I will skip writing edge-disjoint. I assume that they are all edge-disjoints. Edge-disjoint nested cycles. In the same paper, he conjectured that maybe constant suffices to already force a sequence of nested cycle. So you can define the sequence of nested cycle analogously. We have C1, C2 to Ck such that Ci plus 1, the vertex set, is a subset of Ci, is the previous one. So they're sitting really nesting one in another in an iterative way. So, and then he conjectured that maybe this, for some C, depending on K, you have K nested cycles. This was not resolved until quite a while after. I think now this K nested cycle is also known, proved in 1996. By Chen, Erd H, and Staten, they prove that it is indeed the case. Okay. Let me just write true this statement. So maybe I will give you a sketch of the proof. Really, not even a sketch of the idea how they prove this thing.
When they prove it, do they also guarantee that these cycles have even length? Or
they cannot be, because when one sitting inside another, and it's a proper subset with a nestedness, and necessarily the vertex has to shrink, right? So the length gets shorter and shorter. So there's, for example, let me draw one for you. If I take k equal to 3, what they find is something like you have this cycle, the first one, and maybe the second one look like, I don't know, like this, and the third one, edge-disjoint. Maybe, how do I do it? Let me cheat. These two are different edge. Okay, you get the idea. So you really want one sitting in the previous one, and so on and so forth.
Yeah, I'm also. My question is probably the difference. So I was wondering whether they can say all these cycles have even length.
Probably it's not so hard because you can pass to bipartite subgraph while keeping half of the average degree, right? So we can guarantee even, but for odd that would be not so clear. Yeah, for odd usually chromatic number is needed instead of average degree. So I think that would be a harder question. But there is work done on the odd integers as well. So how do they possibly prove such a thing, like k nested one? Sounds quite complicated. As it turns out, the idea it's quite a natural one. All they have to do, here's the idea, and the proof is short as well. The idea is to find, so you have for any graph G with average degree D sufficiently large, then what they do is they found a cycle C, then there exists the cycle C, such that the subgraph induced on the vertex set of this cycle, their average degree diverges with D, grows with D, such that the graph induced under this set of cycles, this graph, let me call it H, has average degree, some, let's say, g of d, function of d, that goes to infinity as d goes to infinity. Why this is enough? Then you can iterate this statement on H to find another cycle inside on the vertex set of which the subgraph induced has sufficiently large average degree, and so on and so on. So you can keep doing this. Of course, the function obtained, I'm not sure if it's optimal, but it does solve the problem. Any questions? So I will only say this much about this proof. So yeah, to be precise, we can take the induced subgraph and then you delete the edge of the cycle. Then only delete on average just linear in n number of edges. It's just -2 here. So this guy still diverges. But that's in, yeah, I forgot to say that. We do have to be precise, you have to delete it so that these cycles are edge disjoint. Right. So, but now if we come back to this proof, there's a problem here. This is why the second question has not been resolved yet. The problem here is that all we know is on this red cycle C, the induced subgraph is dense. But whatever structure you can find inside, we have no control whatsoever. Like we know that there's a cycle inside, but we don't know its shape, how it's going around the vertex set of that, the red ones. So this is why having this no geometric crossing, it's not so clear how we can go about it following this approach. Okay. Where's my? Good. So for the rest of the time, this will be a short talk, most likely. I can already give you the sketch of the proof. So here, let me state the main results. Here's our main result. So we proved that question 2, basically average constant degree also suffices to force 2 edge disjoint cycles, nesting, and the inner one can be drawn without crossing. So for any graph G with average degree some sufficiently large constant, then such thing exists. Exist this kind of nested cycles without crossing. So how we do it? Before I give a sketch of proof, here's an open problem for you. From our proof, it's not so clear how to generalize in this direction. Can you have not even K, even 3 edge disjoint nested cycles, one inside another without crossing, each one of which can be drawn without crossing? It's not so clear how we can do it. It seems like new ideas are needed. Okay, so it will be interesting. Let me write as open problem. Can you guys all see here? Open problem is that, is it true that constant average degree, of course constant depends on K, enough to force K edge disjoint nested cycles without geometric crossing? Enough to force K nested cycles with no crossing. Okay. Any questions before we sketch the proof about the statement, or any comments? How big is the C? Some absolute constant. We didn't compute it, so that's some absolute constant. Oh, it's not regularity constant, so it's really a reasonable constant, not the number of atoms in the universe and beyond. Yeah, it's a reasonable constant, maybe like a million or billion, something like that. Yeah. So. Right, before I dive into the tools and a little bit more details, I try to keep it informal. Let me first tell you the idea. The idea is basically the proof uses sublinear expander, which I will give you a very quick introduction. Using this, the key ingredient, key structure, is what we call Kraken. Have you seen the movie? The crash release the Kraken. Anyone? No one saw this movie? It's basically a giant octopus. In the Greek, yeah. So what do I mean by that? So the idea is we want to build these nested cycles without crossing in a reverse order. Before, what they do here is to find outer one, then make sure that this outer one induce a dense graph. Then you can find one inside, but there's no control on what you can find inside. Now we build the inside one first and outside. So we do things in reverse order. Okay. Before I give a formal definition of the Kraken, basically it looks something like this. It has its body, which is a cycle, and to each vertex on the cycle, it's linked by vertex disjoint paths to balls sufficiently large size, small diameter. So it looks something like this. Hence the name, Kraken. Okay. I think the movie title is called Clash of the Titans or something. So in one of the scenes, all these gods are fighting each other. Then the Zeus side is losing. And then he gets furious. He said, "Release the Kraken." So this is the monster they summoned from some outer space. A giant octopus like this.
It's way more than 8 legs.
That's why it's not just octopus.
Kraken is still enough.
So yeah, so if you look at this structure, all we do is to attach these two balls, well, vertex disjoint path, to the vertex on the cycle. So now you might already guess what we're going to do, how to embed these two cycles without crossing. Suppose we have such structure in place. Suppose we release the Kraken. Okay, then all we need to do now is to link its arm or legs, the consecutive one. Vertex disjointed. Okay. Now what happens is, if you chase these, blue and red ones, it's precisely the outer cycle, isn't it? That will finish the proof. So this is the proof in one sentence. Of course, there's technicality, which I will address.
Why we need cycle in the tip of the leg? Because just one point.
Oh, that's one of the difficulties. This is why we attach a ball, not just a single vertex. I will address this difficulty. That's a good question. Okay, any other questions? So, okay, good. We have the proving animation. Now let's see a little bit more details. So let me give you some formal definition, still rather informally. What is this sublinear expander? Okay. Sublinear expander 101. Yeah. Expander, we all know what it is. It's a sparse, highly connected graph originally designed for networks. If it's sparse, it's cheap, right? And you want to reach one node from another quickly. Or in other words, you want this graph to have some short diameter property. But the traditional one often has, coming from the spectrum gap, they have constant expansion rate. And here, why we call sublinear is because the expansion we're asking for is just only sublinear instead of linear. So the definition, what is a sublinear expander? We say G is a sublinear expander. Let me just call it expander. If for any vertex x whose size is less than half of the order, let me use always little n for the order of the graph, then its external neighborhood, I'll write x, n of x, is at least maybe not growing with x, more or less something like this, x over log x squared. So here, hence the name sublinear. Here's a picture. We have x, and you want its external neighborhood to expand, growing as the size of x grows. So from this, that looks rather weak, but what's useful about this notion is that, one, it's proved by Komlos and Semerady. Back in 90s, I think around 93, that for no matter which graph you give me with average degree d, I can always find within a subgraph whose average degree is d minus little o d. You just lose a tiny bit, such that this subgraph has enjoyed this sublinear expansion property. This is why it's useful. We use this particular notion, is because all this problem we're given that the average degree is large. So just by losing a negligible factor, we can additionally have this expansion property. And one of the immediate consequences of this expansion property is that it's the so-called short diameter property. What it says is the following. For any two set x and y, and maybe there's some obstruction set w, which is comfortably smaller than x and y. Here, whenever I use less than, that just means maybe less than x over some polylog x, okay? Just to be beaten by this expansion. Then we can link this xy up using an xy path or polylogarithmic length, avoiding w. If it's expanded, in an expander. We have that. One, avoiding w, so it's in G minus w. Second, it's short. The length is polylog in n. Here's a picture. You have x and y. and you have some small obstruction W somewhere, it could overlap with X or Y, doesn't matter. Then the proof is very simple. You just keep expanding X and Y. Since W is tiny to obstruct the expansion, then you can link them up like that by keep expanding them. Eventually, they will overlap. Good. So the bulk of the work of the proof is to find this structure, this crack-on. Once you find them, to finish the linking is relatively easy. Basically, you try to use this short diameter property to link them up. So let me mention a couple lemmas we need to embed this crack-on. Maybe I'll leave this picture here. So some lemma about the robust expansion. Here's one lemma. Lemma A. It basically says that we have an expander with a minimum degree D. I will skip writing. Oh, maybe let me just write it. You have an expander, minimum degree D, and you have some set W. You try to avoid. How large is this set? Little o, n over log n squared, say. Not so big, sublinear. And we can always find in G minus W a large ball, disjoint from W, linear sizing and short diameter. Then you can find exist in G minus W a ball, by a ball just a connected set. A ball B of size say n over 100, really linear in n, and diameter is polylogarithmic. Let's say log n to the 4. Okay, at most. So as you might guess, we will use this lemma to once you link some already, then we kick them aside, set them into W, and find in G minus W another ball and try to link it again if you haven't finished the embed. This is how we're going to use this lemma. Okay. The second lemma, lemma B, is the robust exponential expanding of small sets. Of small sets. So how it looks like is informally, it's like this. You have a graph G, which is an expander, say minimum degree D, and you have three sets, X, Y, W. You take an integer at most log n, so what about this set? Such that Y is comfortably smaller than X, say polylogarithmic factor smaller than X, is tiny, as in the W with respect to X, Y here. And W is thin, which I haven't defined you, around X. Then what we know is that you can expand our set X, avoiding both these two sets, Y and W, almost exponentially with respect to the radius of the ball. Let me draw a picture for you. Here's a picture for lemma B. Okay, what it says is the following. I have my set X, which I want to expand. Normally, if there's no obstruction Y or W existing, then you just expand layer by layer. We know by the definition of the sublinear expander, we know that each layer has X over log X, basically, right? But now we have some obstruction coming from Y, but Y is very tiny with respect to X. So Y can only touch each layer so much, 1% at most. So those we can ignore them and keep expanding as before. And there's another set W. W might be bigger than X in the total size. But we also know that W is thin around X. It's basically in the same way that thin means when you expand X, each layer, W, even though it's big itself, but it cannot touch each layer of X while expansion. Formal definition is like this. I can write it down, but not very informatic. So by thin, I mean lambda k thin around X if you look at the neighborhood, when you expand the set X, avoiding W, look at the I minus 1's ball, expanded, intercept with W, this is small, some polynomial in the radius. So this means when you expand this ball, I minus 1 level, right? Here's I minus 1 level. And you expand it inside G, intersecting W, still not so big. The size is polynomial in I. Actually, polynomial is not really any problem. As long as, if you look at this result, as long as it's sub-exponential, you take the derivative, it's smaller than that derivative, that's enough. Okay? Good? For every I less than, for every R less than equal to log n. Yeah. All right, now I can state the main lemma, how we construct such thing. Oh. And then I'm going to come back to address Dungyo's question, why we bother to attach the ball at the end of the arm instead of just having a single vertex. Difficulty number 1 in this connection. Let me try to deliver some idea. What's the possible difficulty? Not to mention that if the end is a single vertex, let's suppose that it's a ball. So draw a simple scenario. Suppose we have this guy, really it looks something like this, and continue. Okay, so this whole thing, the tree coming from here, or the connecting part, it's the ball attached to it. And we have a similar one here. So there is a vertex UI1, UI2, say, for this VI, responsible of the connection point that's in charge of connecting this path with the ball, right? That's the contact point. And you have the ball here. Now, what could go wrong? There's a danger of having this UI1 or I2 getting cut off by previous construction, by previous path. So here's what I mean. Suppose we are building, suppose we already have this structure, the crack-on. Now what do we want to do? We want to find this red path to link them up, right? Okay, how do we find them? We usually just find them greedily, iteratively, one by one. Suppose now I want to link, say, this guy to this guy, right? I want to go here to here, here to here, so on and so forth. But what we use is this. Is the lemma still here? No, I erased it. The short diameter lemma, saying that if you have two large sets, you can link them up by a short path. So in other words, we have no control of how this path could go, where it could go, right? So it could go something like this. Or maybe let me not make it so special. You come here, here, like that. What's the problem now? The neighborhood of UI1 get completely used up by previous path, red path. Now, when it comes to the term of linking this one to this one, we cannot do it anymore. Because, yeah, you can link it, but once you link it, you cannot chase back to complete it to two nested cycles. That's the first difficulty. So perhaps that also explains a little bit why the Donggyal's question, why we want to attach not just a single vertex, because this single vertex is too fragile for the later stage embedding. Okay, now there's a second difficulty which I want to kind of convince you. Let's say need to protect the contacting point. In these pictures, UI1, UI2. The second problem we have to address is how we prove this. So now I can give you a high-level sketch of the proof of this embedding of the Kraken. The high-level stretch is that basically what we do is to first find the shortest cycle in our expander G. Let's call it C. Find the shortest cycle. Now, we repeatedly using lemma B, or maybe rather lemma A, yeah. Use lemma A to set aside, we have this little o of n over log n squared rule to set aside, right? So we set aside whatever structure we found so far, but so far there's nothing. We just set aside this cycle. We can find a large ball somewhere. I don't know where, I don't care where. So I found it, this guy. Then, now the task is to expand some vertex on the cycle, layer by layer, till it's large enough, so then we can use this short diameter to link them up. Why it has to be large enough? We have to make sure that this is comfortably larger than C, so we can avoid touching C while making this blue path linking. Right? We can only avoid some structure if the set we are connecting is polylogarithmic factor bigger than this. So you have to expand them first while not touching C and then link to that. So this is what we're going to do. So where is the second difficulty? Here comes the problem. Suppose we already link some. We have no control on this length of the cycle C. All we know is the shortest cycle, so it's of length. All we know is at most 2 log base d of n. You just do BFS. Then you take twice the depth of the BFS. That's the upper bound on the length of the cycle. So it could very possible that C is of length order of magnitude log n. So C could be log n. Well, the vertex on C could be of degree d, which can be completely nothing related to the order of the graph n. So it could be just a constant. Why is that a problem? The problem is that now we've linked up to log n meaning path. And all these paths now if we want to further expand the vertex, its first layer is only of size constant, right? The degree. So how we can make sure that all these immediate levels are not blocked by previous constructed path? That's the second difficulty. Need to protect, how do you say? Cannot block the immediate neighborhood of the vertices on cycle C. Let me write here. Immediate. Looks a little bit strange. I think the longer you stare at a word, the weirder it gets. Anyway, I'll just leave it like that. Immediate neighborhood of vertices on C in this shortest cycle C. Okay, so I'm running out of time, but maybe let me just address these two difficulties, say very sketchily how we can avoid these difficulties and build this thing. First of all, how we build this guy for the second one, to make sure that the neighborhood of the vertices on C are not blocked. This is how we do it. So this is our cycle C. Suppose V is the current vertex we want to expand and link to some ball somewhere other place. We use lemma A to find. And suppose we already have some structure found somewhere that we need to avoid. So these red ones are the ones we need to avoid. And we want to expand this V. This is the blue picture. Make sure that V still expand away from this red structure together with the cycle C itself. The trick basically is to make sure that all previous flying paths are the shortest possible, together with the fact that C is also shortest. Why this helps? Now, if C intersect this too much, the expansion of V too much, then C was not the shortest cycle to begin with. Look, the first neighborhood, suppose you have 3 vertices here are on C. What does it mean? Apart from possibly these two, there's another neighbor. Then you could have built a shorter cycle. That's a contradiction. So you can use this idea to show that in each level, C is thin around V. Similarly, all these paths, you can prove that they are thin in that definition around this expansion of V. Why? For if it intersects too much, this guy intersects too much and go here, then I could have linked this guy, go a much shorter way to link to this ball. I can replace it with another path that's much shorter while doing the same job, right? Of course, you have to formulate it in a more rigorous way, but that's how we address the second difficulty. For the first difficulty, what we have to do really, I mean, the dream is pretty, but in reality is a bit more technical. What we really have to do is to address this first difficulty, is to do the following. Let me assume, in addition, that the maximum degree of G is only polylog in N, okay? Let me give this additional assumption to make things easier. Suppose that we are in this scenario. Then what we really do to find this crack-on is that we find this structure such, in addition, all these balls that we attach to the vertex of the cycle, they are pairwise far apart, at least a square root log n apart. So they are pairwise very far apart. Why is that helping us? If they are far apart, then you can expand this whatever you want to connect, say up log n to the power 10, say, levels, you expand them, then you can, these two blue balls will be so large after log n to the power 10 compared to the union of all other things. So you can comfortably avoid them altogether to make this linking. Let me make it red. Okay. Previously, why we can avoid, these are the same size. So you cannot say this can avoid that. We have one has to be bigger than the other by polylogarithmic factor to be able to avoid that. This further expansion step is to do that. And if they are far apart, you just need to expand a little bit more. They are still disjoint since they are far apart. Okay? Just one last word. If this is not the case, what we do is that you link this vertex to a high degree vertex instead of a large ball with short diameter. Then that will do the same thing. High degree vertex is actually even easier. So this is like a low quality version of high degree vertex, basically. So I think I will conclude my talk here.
Question?
Yep.
When you find these tested cycles, do you have any control over the relative size of them? Did you say you want the smaller ones to
All we know is they are both just polylogarithmic size. That's the only control we have. It could be that the graph itself is expander and has logarithmic girth, and that's the best we can say. Yeah. So you cannot guarantee, say, any constant, something independent of n.
So what's the difficulty to extend this idea to find the three nested cycles?
So you have to come up with some structure more complicated than the Krekon. Here, you see, you do this linking. But if you want to do one more time, all these vertices here, they are part of the outer cycle, has to also be linked to something else. Right? It's mutating really fast. You need to find something that's mutating as fast as that. And we couldn't make it work. It seems like maybe you have to do some other approach. It's not clear.
So for the cycle, you have to choose specifically, right? Like minimize length and blah, blah, blah.
Yes. To make sure that we can really expand the vertices on the cycle for later connection. Yeah.
I was imagining that if you were trying to solve for 3 nested one, maybe you try to expand into the like fix one and then you try to build outside one and inside one. But as long as you have a large density inside, it may that is a kind of thing with ordering. Then there's an issue about the length of the cycle. So
I think definitely new ideas are needed. It's not clear to me. Yeah.
So those balls you are making, they are of size n/1 concept?
Or you can shrink them to down to the size that you want. You can tailor it if you want, trim them down. Is that your question?
Like, I'm a bit confused about like, so the small cycle, that can be like as large as like log n, right, or something like that.
It could be as large as log n.
And
And we only attach these, say log n to the 10 is enough. So everything here altogether is only log n to say 11 power or something, right? So when you expand this blue ball to log n to 100, it's big enough to exclude everything.
any other questions? Okay, now let's thank the speaker again.